Okay, so the first thing I want to talk about today is impulse. We briefly looked at this last lesson. Impulse basically is the change in momentum. And if you remember, we had an equation for it, which is that I, impulse, equals the final momentum subtract the initial momentum. Okay, and we can write this in a slightly more usable form of m brackets v minus u. Now the units of impulse are Newton seconds, not Newtons per seconds, but Newtons times seconds. So another way of thinking about impulse could be that we are looking at force times time. Okay, so another way of thinking about it is it's the force we apply times by the time it's being applied for. And the first thing I want to do is basically look at an example with you to see how this works, and also tie together acceleration and force with impulse. So over here, I have a still from a video of a golf club hitting a golf ball, and you can see the golf ball's deformed slightly as it hits it. You may have seen a similar video, a bit more extreme, of a golf ball sort of flattening. And if you use high-speed photography, you can absolutely see the deformation of a ball like this. It's very interesting. However, what I want to look at is how we can work out the ball speed of a golf ball when it's struck, and see how we can bring impulse into that. So I'm just going to get rid of these last two little bits. Okay, so let's set this up. So let's imagine I have a golf ball. Here's my golf ball, and I've got my club here, which is going to be a very rudimentary drawing of a golf club. Anyway, here's my golf club, and it's going to hit the ball. Now, a few things to take into account. It is going to hit the ball with a force of 8,000 newtons, and the contact time, as in the time in which the two are together, like is shown over here on the right, is 0.0005 seconds. Okay, so a very, very short amount of time to apply this force over. Okay, well, we've got this. What else do we need? Well, we probably need to know what the mass of the golf ball is. So that is 46 grams. Okay. And with this information, I should be able to work out the impulse. So let's draw my impulse equation. Now we know the initial speed of this golf ball is 0. Okay, it's not moving. If I draw a kind of dotted line here, maybe, that's going to be my v. Okay, so that's when it is moving. So let's look at this equation. So my impulse equals mass. Now mass of 46 grams is going to be 0.046 kilograms. Hopefully you agree with that. And I have v, which is my final velocity, minus 0, which is my initial velocity. So I can straight away tidy up this right-hand side, 0.046 times by v, okay, because the 0 disappears. Now the impulse, well, I actually know what the impulse is, because remember the impulse can be considered to be the force times by the time. Okay, so the force times by the time it is applied over. So the impulse is also equal to 8,000 multiplied by 0.0005 seconds. Okay, so what I'm going to do is I'm going to combine these two equations. So I'm going to write 8,000 times by 0.0005, which is my impulse, and that equals the other way of defining my impulse, which is 0.046 times by my velocity. So you can check this yourself on your calculator. I suggest that you do, to make sure that I'm not barking up the wrong tree. I'm going to check it myself. So I'm going to do 8,000 times 0.0005 and divide that by 0.046. And that gives me a velocity in meters per second of 86.95 So let's call it 87 meters per second. Okay, so there's a way of using impulse to find an answer. And if we think about this, 87 meters per second, well, this actually, if you work it out, if I just work it out in miles per hour really quickly, I can times by 60 for minutes, times by 60 again for hours, divide by 1,000, and then divide that by 1.62. So in miles per hour, this is about 193 miles per hour, which is pretty quick. Okay, that's pretty quick. Now, that's one way of thinking about this. Okay, so we've using the impulse equation to find the speed. And hopefully that makes a bit of sense. It's an impulse over a certain time. Okay, if this time was 0, there would be no impulse. Okay, if this time was longer, there'll be more of an impulse. Let's think about this with force and acceleration as well. So what we should think about is, if I draw a kind of bracket here, and this is my ball, then if I draw the time that they're together as being obviously 0.0005 seconds. So for this bit here, this zone here, which I'll highlight, green, so this zone here, when they are together, that is when the ball is accelerating. Okay, at no other point is the ball accelerating. Once it's together, once it separates from the club, it's no longer accelerating. Actually, it will straight away start decelerating. So can I work out the acceleration in here of the ball? So to do that, I probably want to think about a suvat. So I'm going to use v equals u plus at. Okay, I know my final velocity. My final velocity is 87. My initial velocity is 0. My time is 0.0005 seconds, and my acceleration is a. So I end up with an equation like this. Okay, and as you can see, this is going to give me quite a big number. So if I divide my velocity by the time it's taken to get from 0 to that velocity, they end up, again, check this on your calculator, I've made it 174,000 meters per second. Okay, what that literally means is, if I was to be in contact with this force for a whole second, I'll be going at 174,000 meters per second. Okay, so we can see now why that contact time is so small. And what I want you to think about is any situation where you hit a ball or kick a ball or hit a ball with a golf club, anything like that, the time that they're in contact is when you're accelerating. Okay, as soon as they are not in contact, the acceleration is over and the ball has a velocity. Okay, so it's very similar to our impulse. Okay, we give it an impulse for a time, and once that time is over, the ball is away and it is going at its velocity. Okay, so that's impulse. Okay, so we'll have a little think about elastic and inelastic collisions now. So I'm just going to move the page down, and I'm going to move this photo in here just for reference. Okie dokes. So you can always watch this video back, for reference at any point. So elastic versus inelastic collisions. Okay, so impulse comes into this, but for the moment I'm just going to think about the two types of collisions that we're going to be dealing with. So elastic and inelastic. And in fact, we have sort of three types. We have 100% elastic. We have 100% inelastic. And we have partially inelastic. And actually, of all these three, this one here is the only realistic sort of collision. Okay, the other two are very much theoretical. Totally inelastic and totally elastic. Okay, well, what are these? What's the difference? Well, here's a kind of photo to show you what the difference is. If I just click on this GIF, you'll be perfectly sort of aware of this here, which is Newton's cradle. This would be an example of 100% elastic collisions. Okay, now the reason for that is that all of the kinetic energy is transferred through. I'll talk to you about this briefly in a moment, because Newton's cradle is actually a bit of a weird one. It doesn't actually work how you think it does, but it's a nice visual thing to look at. Here would be an example of an inelastic collision. Okay, maybe getting towards 100% inelastic. Okay, two cars crashing head on, and they deform at the front. Okay, they're not going to bounce back like snooker balls. Okay, they will stay together. They may deflect a little bit. Okay, but in this case, we have an inelastic collision. They're not going to bounce back from this. They'll stay in place. So it's probably not 100%, but it's, you know, probably, I don't know, more than 90%. Okay, definitely. Okay, so that's an inelastic collision. That's an elastic collision. Let's have a little look at what actually changes. Okay, because there's one major difference between the two of them. And what we'll do is we'll have a look at a collision lab to see this. So you can use this yourself. It's a really, really good simulation. I can change the elasticity on the right hand side. Okay, so I'm going to go 100% elastic, because that's what we've been looking at so far. So 100% elastic collisions, nice and straightforward. So here I have two particles. My first particle is 3 kilograms. My second particle is 2 kilograms. This one's going at 1 meter per second. This one's going at 3. So I can look at my momentum diagram down here, and I can see that, well, I have a total to the right. So when I play this through, and also notice I have kinetic energy of 10.5 joules overall. Okay, so when I play this through, they collide and they go off, and afterwards we can see our momentum is exactly the same. Okay, so momentum is conserved. Look at our kinetic energy. Our kinetic energy is exactly the same as well. Okay, so let's change this. Let's change the elasticity to 50%, and let's reset this. Is it going to let me reset it or not? Probably not. Okay. Let's have a look. So it was, before it was 1, and this one was -3, wasn't it? Okay, so let's move these apart again. So we're starting with the same situation. The initial kinetic energy is 10.5. The elasticity is 50%. So let's see what's different. Okay, again, the momentum, that looks okay. Let's play it through. Okay, straight away you'll notice they're going away from each other slower. The first thing to notice is that momentum is exactly the same. Okay, that is conserved. Here's the important bit though. The kinetic energy is less, 3.3 joules. Okay, so if I, it doesn't let me reset it, okay. If I make it even more inelastic, if I make it close to being, well, 100% inelastic, here we go. Let's see what happens there. Again, kinetic energy beforehand is 10.5. The momentum is going to be conserved. Okay, and as you can see, they join together. So there's no deflection at all. They join together and they move off as one unit. The kinetic energy is much, much less. The momentum, however, is the same. Okay, so for each one of these situations, the momentum is conserved, but the kinetic energy is different, and that's all down to this elasticity. So, going back to this, if I have an inelastic collision or an elastic collision, let's compare them. So, elastic and inelastic. So for both of them, okay, the conservation of linear momentum is true. Okay, in other words, momentum is conserved. Okay, so for both, momentum is conserved. And that is really important because in your calculations, you'll need to use your M1U1 plus M2U2 equals M1V1 plus M2V2. So in all situations you're going to come across, momentum is always conserved. Okay, so that's the same. Okay, however, the kinetic energy is not conserved. So for an elastic collision, okay, kinetic energy is conserved, whereas in an inelastic collision, kinetic energy is lost. Okay, we get a reduction in kinetic energy. And this is because of a number of things. It's because of sound and it's because of heat. Okay, so we have energy losses. Now this is really, really important. In an inelastic collision, if it is partially or 100% inelastic, we lose kinetic energy. Okay, whereas in an elastic collision, we conserve the kinetic energy. It stays exactly the same. Okay, so when you do your calculations, you need to factor that in and be really, really careful. Now, one last thing to talk about is the I'm in red. Is the coefficient of restitution, which we call E. Now the coefficient of restitution we have come across before. Basically it's how bouncy or how springy something is. Essentially it's how much, if I dropped a ball on the floor, for example, and we've looked at this before, how far it comes back up, okay, is a good indicator of the coefficient of restitution. And if I keep bouncing a ball on the floor, it will get lower and lower and lower. Okay, and it will form this nice trend like this. Okay. Coefficient of restitution, it goes between 0, it has to be more than 0, but it can be 1, so it's less than or equal to 1. So that's the range of values for it. And it is broadly defined as the speed of separation of two particles divided by the speed of approach. Another way of looking at that is the speed of rebound over the speed of approach. Okay, if we're thinking about a ball hitting the floor or a ball hitting a wall. Okay, now this value here, the coefficient of restitution, is going to determine basically how elastic or how inelastic a collision is. Okay, so if something is has a value of 1, then 1 means 100% elastic. Okay, whereas 0 means 100% inelastic. So they're going to stick together like Play-Doh or like clay coming together. Okay, I thought I'd show you something here which is quite interesting. Here's an example of something which has a 97% coefficient of restitution. Okay, and as you can see, it takes a long time to decay. This is simply a bouncy, well, it's not actually a bouncy ball, it's a solid ball on a sort of trampoline. Okay, so we have in this situation a coefficient of restitution that's really high. Okay, so it's close to being 100%. Okay, it goes on for a while. So a few things to think about today, and things you're going to use. You need to use your impulse and think about that. This equation here. Okay, make sure you are happy with how this one works. Okay, you will also need to factor in and think about elastic and inelastic collisions. Remember, for an inelastic collision, the difference is that kinetic energy is lost. Okay, and inelastic factors in coefficient of restitution. And the final thing to think about is your speed of rebound and speed of approach. Now, the very last thing I want to talk to you about is our Newton's cradle, because it is an interesting one. If I have my balls on a Newton's cradle, Okay, and this one, you've all seen this before, this one comes in, hits this one, and this one here, as a result, goes off. Now this is something you can look into yourself in your own time. This has actually got very little to do with momentum. So it's not really about momentum at all. Okay, it's actually all to do with these distances. So as a bit of a challenge for you, I would like you to maybe do some research and find out actually how this works. Okay, so in your own time, how does a Newton's cradle work? Okay, I'll be really interested to see how you get on with this, because actually it's a really, really interesting thing, and it goes against a little bit what you expect. Okie dokes, right, you're going to have work to do. I'll be with you the rest of the lesson. At this point I'm going to say goodbye, but you can watch this back on your phone if you need to. Ta-ra now, bye-bye.